On the largest scale, the universe is supposed to be simple, not chaotic, not irregular, but smooth, uniform, predictable. According to modern cosmology, matter in the universe should be distributed evenly when viewed across vast distances. Galaxies may cluster together locally. They may form group and cluster, but beyond a certain scale, everything should begin to look the same. This idea is known as the cosmological principle. It is one of the foundations of our understanding of the universe. It tells us that no matter where you are, the large-scale structure of the cosmos should appear roughly identical. But what if that assumption is wrong? Over the past few decades, astronomers mapping the distributions of galaxies across the universe have discovered something unexpected, something enormous, structures so vast that they stretch across hundreds of millions, even billions, of light years, worlds of galaxies, filament connecting clusters across unimaginable distance, regions where matter appears far more concentrated than our model predict. One of the most striking examples is a structure known as the Hercules corona Borealis Great Wall. This immense formation is estimated to span over 10 billion light years. To put that into perspective, the observable universe itself is about 93 billion light years across. This means that the single structure may extend across more than a tenth of the entire observable cosmos. According to our current understanding, structure of this size should not exist. The law governing the growth of cosmic structure, shaped by gravity, dark matter, and the expansions of the universe, impose limits on how large such formations can become. Beyond a certain scale, matter should smooth out. Irregularities should disappear, and yet they do not. The universe appears to contain structure far larger than expected, and the Hercules corona Borealis Great Wall is not the only one. Astronomers have also identified massive formations such as the Sloan Great Wall and the huge large Quasar group. Each of the discoveries raised the same unsettling question. But how did structure this large form? Because in the early universe, matter was distributed almost perfectly evenly. Tiny fluctuations in density, remnant from the Big Bang, grew over time as gravity pulled matter together. Galaxies formed, clusters emerged, filaments stretched across space. But according to our model, there should be a limit, a scale beyond which structure cannot grow any larger. And yet, observations suggest that this limit may have been exceeded. If the giant structures are real, and if their size are confirmed, they may challenge one of the most fundamental assumptions in cosmology. They may force us to rethink how the universe evolved, how matter is distributed across cosmic scale, and whether the universe is truly uniform after all. Because if the cosmos contains structure this vast, it may not be as simple as we once believed. It may be more complex, more uneven, and more mysterious. Some scientists argue that the discovery could point to unknown processes in the early universe. Others suggest that our models of cosmic structure formations may be incomplete, and a few have even proposed that these enormous structures could be statistical anomalies, rare but possible fluctuations in an otherwise uniform universe. But the truth is, we do not yet fully understand them. Somewhere across the cosmos, galaxies are arranged in patterns so vast that they stretch the limit of human comprehensions, structures so large that they blur the boundary between order and randomness. And every new map of the universe reveals more of this hidden architecture, a cosmic web of matter connecting galaxies across billions of light years, a structure so immense that we are only just beginning to see it. And if the giant formation truly should not exist, then what's all about the universe have we misunderstood? To understand why the giant structures are so puzzling, we must first understand how the universe is supposed to look on a larger scale. According to modern cosmology, the universe began in an almost perfectly uniform state after the Big Bang. In those early moments, matter and energy were distributed nearly evenly across space, but not completely. There were tiny fluctuations, slight variations in density, so small they were almost imperceptible. These fluctuations are preserved in the faint afterglow of the early universe known as the cosmic microwave background. When astronomers study this ancient signal, they see a nearly uniform field with minute temperature variations. These variations represent the shift of our future cosmic structure. Over billions of years, gravity began to amplify the tiny difference. Regions that were slightly denser attracted more matter. As matter accumulated, gravity strengthened. This process continued, gradually pulling matter together into larger and larger structure. But ordinary matter alone cannot explain how quickly these structures formed. This is where one of the most mysterious components of the universe becomes essential, an invisible substance known as dark matter. Dark matter does not emit light. It does not interact with electromagnetic radiation, but it exerts gravity. And in the early universe, it played a crucial role. Dark matter began collapsing into dense regions long before ordinary matter could. It formed the gravitational scaffolding upon which galaxies would later assemble. As ordinary matter fell into the dark matter halos, the first star and galaxy began to form. Over time, these galaxies did not remain isolated. They grouped together into clusters. Clusters connected to form larger structure, and eventually, these structures stretched across vast distance, creating what astronomers now call the cosmic web. The cosmic web is one of the most remarkable patterns in nature. Galaxies are not scattered, randomly through space. Instead, they traced out enormous filament, long, thread-like structure connecting clusters of galaxies. Between the filament lie vast empty regions known as void, where few galaxies exist. If we could step back and view the universe on its largest scale, it would resemble a three-dimensional web, a network of matter stretching across billions of light years. This structure has been confirmed through large-scale surveys such as the Sloan Digital Sky Surveys. By mapping the positions of millions of galaxies, astronomers have been able to reconstruct the architecture of the cosmos, and what they see closely match theoretical predictions, at least up to a point, because according to our current model, there is a limit to how large the structure can grow. The expansions of the universe act as a counterforce to gravity. As space expands, it pulled galaxies apart. On sufficiently large scale, these expansions should prevent matter from clumping together into ever larger structure. This led to an important prediction. Beyond a certain scale, roughly a few hundred million light years, the universe should appear homogeneous. In other words, if we zoom out far enough, the distributions of matter should smooth out. No structure should dominate. No region should stand out as significantly different from another. This is a direct consequence of the cosmological principle, and for many years, observations seemed to support this idea. The cosmic web revealed filament, cluster, and void, but all within expected limit. Nothing appeared large enough to challenge the fundamental assumptions of cosmology, until astronomers began discovering structures that seemed to exceed those limits. Structures so vast that they stretch across scale where the universe should already be uniform. Structure that appear to violate the very principle used to describe the cosmos. If the cosmos web is the blueprint of the universe, then the giant formations may represent something unexpected within that design, something that does not fully fit, and understanding why they exist may require us to look deeper into the origins of cosmic structure itself, because the universe we observe today may not be as simple or as uniform as we once believed. For decades, the large-scale structure of the universe appeared to confirm one of the most fundamental ideas in cosmology. The cosmological principle seemed to hold true. Galaxy forms cluster connected into filament, and beyond a certain scale, everything appeared to smooth out. But as astronomical surveys become more detailed, subtle inconsistencies began to emerge. At first, these anomalies were easy to dismiss: small irregularity, local variations, statistical noise. But over time, the data became harder to ignore. One of the earliest hints came from the discovery of unusually large galaxy grouping that extended farther than expected. Among them was the Sloan Great War, stretching across more than a billion light years. It was already pushing the limit of what cosmological model predicted. Yet it was still considered just purely within acceptable bound. Then came something even more surprising. Astronomers studying distant quasar, extremely bright objects powered by supermassive black hole, identified an enormous structure known as the Huge Blast Quasar Group. This structure appeared to extend across over 4 billion light years. At that scale, the universe should already appear uniform, and yet here was a coherent structure spanning distance far beyond that limit. This raised serious questions. Was this simply a rare statistical fluctuations, or was something fundamentally missing from our understanding of cosmic structure? Then came one of the most controversial discoveries of all, the Hercules corona Borealis Great War. This immense structure, identified through the distributions of gamma-ray bursts, may span up to 10 billion light years. If confirmed, it would be one of the largest known structures in the observable universe, and it would stand in direct tension with the predictions of modern cosmology, because according to current model, structure of this size should not exist. Gravity alone should not be able to assemble matter across such vast distance. The expansions of the universe should prevent such large-scale currents. Yet, observations suggest otherwise. These discoveries represent what scientists sometimes call crack in a theory, not outright contradictions, but anomalies, observations that do not fit neatly within existing model. And in science, such cracks are often where new discoveries begin. Some researchers argue that these structures may not be as coherent as they appear. They could be the result of projection effect, distant objects that appear connected from our point of view but are not truly part of a single structure. Others suggest that the statistical methods used to identify these formations may exaggerate their significance. But even with the uncertainty, the pattern remains. The universe appeared to contain structures that are larger, more complex, and more extreme than expected. And if these structures are real, they may point out to something deeper, something about the early universe, something about the distributions of matter, or something about the fundamental law that govern cosmic evolutions. Because if the universe truly contained structure this vast, then the assumptions we use to describe it may not be complete, and the cosmic web we thought we understood may be hiding something far more extraordinary. To understand whether these enormous cosmic structures are real, astronomer first has to answer a difficult question. How do you map something as vast as the universe itself? Unlike planets or nearby stars, galaxies are scattered across immense distance. We cannot observe the universe from the outside. We are embedded within it. which means every map we create must be built from our limited perspective on Earth. The challenge is enormous, but over the past few decades, astronomers have developed powerful techniques to reconstruct the large-scale structure of the cosmos. One of the most important tools in this effort has been massive sky surveys, project designed to observe and catalog millions of galaxies across large regions of the sky. One of the most influential of these is the Sloan Digital Sky Surveys. Using a dedicated telescope, the surveys has measured the positions and distance of millions of galaxies, creating one of the most detailed maps of the universe ever constructed. But mapping the universe required more than just knowing where galaxies are. Astronomers must also determine how far away they are. To do this, they rely on a phenomenon known as redshift. As the universe expands, light from distant galaxies is stretched toward longer wavelengths. The farther away a galaxy is, the greater its redshift. By measuring this effect, astronomers can estimate the distance to each galaxy and reconstruct a three-dimensional map of the cosmos. When these data are combined, a remarkable picture emerges. Galaxies are not randomly distributed, but they trace out vast filaments and whorls, separated by enormous void. This structure closely resembles the predicted cosmos web, but within this web, astronomers began noticing something unexpected. Certain regions appear far more extended than predicted. To confirm the structure, scientists needed additional methods. One approach involved studying quasars, extremely bright objects powered by creating supermassive black holes. Because quasars are so luminous, they can be observed across vast distances. By mapping their distribution, astronomers can trace large-scale structures that might otherwise be invisible. This is how structures like the huge large quasar group were identified. Another method involves studying transient cosmic events. Among the most useful are gamma-ray bursts. These brief but powerful flashes of gamma radiations can be detected from extremely distant galaxies. By analyzing the locations of many gamma-ray bursts, astronomers can infer the distributions of matter across large regions of space. This technique played a key role in identifying the Hercules corona Borealis great whale. But mapping such enormous structure is not straightforward, because the farther we look into space, the further back in time we are observing. Light from distant galaxies may have traveled for billions of years before reaching Earth. This means that different regions of our cosmic map represent different epochs in the universe's histories. We are not seeing a single snapshot. We are seeing a layered timeline, a patchwork of cosmic history stitched together from light emitted at different times. This complicates the interpretations of large-scale structure. What appear to be single continuous formations may actually consist of objects that existed at slightly different times. Projections effect can also create the illusions of structure. Objects that appear close together in the sky might actually be separated by vast distance along our line of sight. To address the challenges, astronomers use statistical methods to determine whether observed structures are likely to be real. They compare observational data with simulation based on current cosmological model. These simulations incorporate the effect of gravity, dark matter, and cosmic expansion to predict how structures should form over time. If the observed structure match the simulation, the model are confirmed. If they do not, something may be missing from our understanding. And this is where the mystery deepened. In many cases, the largest observed structure appears to boost or even exceed the limit predicted by these simulations. Some structure may still fall within the range of rare statistical fluctuations, but others appear increasingly difficult to explain. This has led scientists to consider new possibilities. Perhaps the early universe contained larger density fluctuation than previously thought. Perhaps dark matter behaved differently on a larger scale, or perhaps the assumptions underlying the cosmological principle needs to be re-examined because if the universe is not truly uniform, then the map we are building may be revealing something far more profound, a cosmos with structure on scale we never expected, a universe whose architecture is more complex than our model predict, and a mystery that continues to grow with every new observations. As evidence for enormous cosmic structure continued to accumulate, astronomers faced a difficult realization. The universe might be more complex than their model predicted, but before abandoning established theories, scientists began searching for explanations within the existing framework of cosmology. Could the giant structure still be consistent with what we already know? One possibility lies in the role of dark matter. Dark matter makes up most of the matter in the universe. It does not emit light, but its gravitational influence governs how galaxies form and cluster. In the early universe, dark matter began collapsing into dense regions, forming halos that acted as seed for future structure. These halos merged over time, creating larger and larger formations. Within the framework, the cosmic web emerged naturally. Filaments of dark matter connect clusters of galaxies, forming a vast interconnections network across space. But even within this model, there are limits. The growth of structure is constrained by the expansions of the universe. As space expands, it counteracts the pull of gravity, preventing matter from clumping together indefinitely. This sets a natural scale for how large structure can become. So, how do we explain structure that appear to exceed that scale? One possibility is that the formations are not truly single, coherent structure. Instead, they may be composed of smaller structures aligned along our line of sight. From our perspective, they appear connected, but in reality, they may not be physically bound across their entire length. This explanation is known as a projection effect. It suggests that some of the largest structures may be visual illusions created by the way we observe the universe. Another possibility involves statistical fluctuations. Even in a universe that is uniform on average, random variations can occur. Given a large enough sample, rare events become inevitable. Some scientists argue that structures like the huge large quasar group may represent extreme but still possible fluctuations, unlikely but not impossible. However, as more large structures are discovered, these explanations become less satisfying. If these formations were truly rare, we would expect to find only one or two. Instead, astronomers are identifying multiple structures approaching or exceeding the predicted limit. This has led researchers to explore more fundamental explanations. One idea involved the conditions of the early universe. The tiny density fluctuations observed in the cosmic microwave background are believed to be the seat of all cosmic structure. But what if the fluctuations were not entirely random? What if one of the largest scale, there were patterns or colorations that we have not yet fully understood? Some theories suggest that processed during cosmic inflations, the rapid expansions that occurred fractions of the second after the Big Bang, may have introduced subtle anisotropy into the universe. The anisotropy could have influenced the distributions of matter on the larger scales, leading to the formations of unusually large structure. Another possibility involves the nature of dark matter itself. Although dark matter is the central component of cosmology, we still do not know exactly what it is. If dark matter behaves differently than current model assumes, perhaps interacting in subtle way or forming structure more efficiently, it could alter the growth of large-scale structure. There is also the influence of dark energy. Dark energy dominates the large-scale behavior of the universe, causing its expansion to accelerate. This expansion limits the growth of structure, but if the property of dark energy have changed over time, or if our understanding of it is incomplete, it could affect how structure form and evolve. Some researchers have even proposed that the largest observed structure may hint at new physics beyond the standard model of cosmology. Perhaps the assumptions underlying the cosmological principle are only approximately true. The universe may be mostly uniform, but not perfectly so. There may be subtle variations on the largest scale that we are only now beginning to detect. In this view, the giant structures we observe are not violations of the rule. They are clues that our current understanding is incomplete, but there is also a more cautious perspective. Some scientists argue that the data itself must be interpreted carefully. Mapping the universe is an extraordinarily complex task. Observational bias, selection effect, and statistical uncertainty can all influence the result. What appears to be a massive structure may, upon closer examinations, resolve into smaller components. This is why ongoing and future surveys are so important. New instruments are collecting more precise data than ever before. With larger dataset and improved analysis techniques, astronomers will be able to test whether these structures are truly as large as they appear, or whether they are artifacts of our observational limitations. For now, the answer remains uncertain. The giant structure observed across the universe may be illusions created by perspective, rare statistical anomalies, or evidence of new physics. Each possibility carries profound implications. If they are illusions, then our current model remains intact. If they are anomalies, then the universe may be more varied than expected, but still fundamentally understood. But if they are real, if the structure truly exceeds the limit imposed by our theory, then we may be missing something fundamental about how the universe works. And this possibility is what makes this mystery so compelling, because hidden within these enormous cosmic formations may be clues to the deepest questions in cosmology. Questions about how the universe began, how it evolved, and whether the principle we rely on to describe it are truly universal. If the largest structure in the universe truly exceeds the limit predicted by our model, the implications reach far beyond astronomy. They strike at the very foundations of the cosmology itself. At the heart of the modern cosmology lies the cosmological principle. This principle tells us that when viewed across sufficiently large distance, the universe should appear uniform. No special directions, no special locations. The law of physics should apply equally everywhere. This assumption is not just philosophical, it is built into the equations that describe the expansions of the universe. It underlies our interpretations of observations, and it forms the basis for model of cosmic evolutions. But what if it is only approximately true? What if, on a larger scale, the universe is not perfectly uniform? The discovery of enormous structures like the Hercules corona, Borealis Great Wall challenges this idea. If such structures are real and coherent, they may indicate that matter is distributed unevenly across scale, whether uniformity should already dominate. In other words, the universe may contain regions that are fundamentally different from others. This possibility carries profound consequences. If the universe is not truly homogeneous, then some of our most important measurements may not be reconsidered. For example, astronomers measure the expansion rate of the universe, known as the Hubble constant, by observing distant galaxies. The measurement assumes that the universe behaves the same way in all directions. But if large-scale structures introduce variations in density, they could influence the measurement. Different regions of the universe might appear to expand at a slightly different rate. This could help explain one of the most puzzling problems in modern cosmology, the disagreement between different measurements of the Hubble constant. Another implications involve the nature of dark energy. Dark energy is thought to act uniformly across space, causing the expansions of the universe to accelerate. But if the distribution of matter is not uniform, it could affect how dark energy influences different regions. This raised the possibility that dark energy itself may not behave exactly as we expect. Perhaps its effects vary across cosmic scale, or perhaps our interpretations of cosmic expansions is incomplete. There is also the questions of the early universe. The large-scale structure we observe today grew from tiny fluctuations in density that existed shortly after the Big Bang. These fluctuations are recorded in the cosmic microwave background, which appear remarkably uniform. But if enormous structure exists today, it suggests that though initial fluctuations may have evolved in ways we do not fully understand, perhaps the early universe contains subtle patterns that are not visible in current observations, or perhaps new physical processes influenced the growth of structure over time. On an even deeper level, these discoveries raise philosophical questions about our place in the universe. If the universe is not uniform, then our locations may not be entirely typical. We may exist in the regions with properties that differ from the cosmic average. This challenges the long-held assumption that Earth does not occupy a special position in the cosmos, an idea that has guided astronomy since the time of Copernicus. Yet scientists approach these implications with caution. Extraordinary claim requires extraordinary evidence. Before rewriting the foundations of cosmology, astronomers must be certain that the giant structures are real, that they are not artifacts of observations, not statistical anomalies, not illusions created by the way we map the universe. This is why ongoing research is so important. New surveys are collecting more detailed data. Simulations are becoming more sophisticated, and new methods are being developed to test the limits of cosmic structure. For now, the evidence suggests that the universe is still broadly consistent with the cosmological principle, but the presence of these enormous structures hints that the story may not be complete, that there may be subtle deviations, small cracks in our understanding that could eventually lead to new discovery. Because throughout the history of science, it is often the anomalies, the observations that do not quite fit, they lead to the greatest breakthrough. The unexpected motions of planets led to the discovery of gravity. The irregular orbit of Mercury led to Einstein's theory of relativity. And today, the largest structure in the universe may be pointing toward something we have not yet fully understood, something hidden within the fabric of the cosmos itself. For centuries, humanity has tried to understand the structure of the universe using the tool available at the time, from early star chart drawn by hand to modern digital map containing millions of galaxies. Each generation has seen the cosmos with greater clarity, and yet the largest structure in the universe remain only partially understood. But that is about to change. A new generation of telescope is beginning to transform the way we observe the cosmos. One of the most ambitious of these is the Vera C. Rubins Observatory, located in Chile. This observatory will conduct a decade-long surveys of the sky, capturing vast amounts of data about billions of galaxies. Its mission is simple but profound: to map the universe in greater detail than ever before. By tracking how galaxies are distributed across space and time, scientists hope to refine our understanding of the cosmos web. This will allow astronomers to test whether the giant structures we observe are truly coherent, or whether they are artifacts of limited data. At the same time, space-based observatories such as the Hercules Space Telescope are focusing on one of the most mysterious components of the universe: dark matter. By mapping how dark matter is distributed across vast cosmic distance, Euclid will help reveal the hidden scaffolding underlying galaxy formations, because the visible structure we observe, galaxy, cluster, and world, we only part of the story. Beneath them lies an invisible framework that determines how matter is arranged. Understanding that framework may be the key to explaining why some structures appear larger than expected. Another powerful tool in this effort is gravitational lensing, a phenomenon predicted by Einstein's theory of relativity. Massive objects bend the path of light traveling through space. By measuring how light from distant galaxies is distorted, astronomers can map the distributions of matter, both visible and invisible. This technique provides a way to study the universe independent of traditional galaxy surveys, and it may help confirm whether the largest structures are truly as massive and extended as they appear. Future radio observatory will also play a critical role. Projects such as the Square Kilometre Array will allow scientists to trace hydrogen gas across vast cosmic distance. Hydrogen is the most abundant element in the universe, and by mapping its distributions, astronomers can track the large-scale structure of matter over time. This will provide a new way of studying the cosmic web, one that is not limited to galaxies alone. Together, these instruments will generate an unprecedented amount of data: billions of galaxies, trillions of data points, a three-dimensional map of the universe extending deeper into space and further back in time than ever before. With this data, scientists will be able to test the limit of current cosmological model. They will be able to determine whether the cosmological principle truly hold, or whether subtle variations exist on a larger scale. they will also be able to refine measurement of the Hubble constant, potentially resolving long-standing discrepancy, and perhaps most importantly, they may finally determine whether the giant structures observed today are real. If they are confirmed, it could signal the need for new physics, new model of cosmic evolutions, new insight into the nature of dark matter and dark energy. But if they are not, if improved data reveals that the structures are smaller or less coherent than they appear, then our current understanding of the universe may remain intact. Either way, the outcome will be significant because we are entering an era where the structure of the universe can be mapped with extraordinary precision, an era where questions that once seemed impossible to answer are finally within reach. And as we refine our view of the cosmos, we may discover that the universe is either more orderly than we feared, or far more mysterious than we ever imagined. When we look up at the night sky, it feels simple. Stars scattered across darkness, galaxies drifting through space, a universe that appeared vast but orderly. For centuries, humanity believed that on the largest scale, the cosmos must follow simple rules. Yet, beyond the complexity of stars and galaxies, there would be uniformity, a smooth, predictable structure governed by universal law. This idea became the foundations of modern cosmology. The cosmological principle. It tells us that no matter where we are in the universe, the view should be essentially the same. No special places, no preferred directions, just a cosmos that looks identical in every direction when viewed from far enough away. But as we have learned more about the universe, that simplicity has begun to fade. The cosmic web revealed that galaxies are not randomly distributed. They form vast filaments and clusters, patterns stretching across unimaginable distance. And within that web, astronomers have found something even more surprising: structures so large they seem to challenge the very idea of uniformity. The Hercules corona, Borealis Great Whale, the Sloan Great Whale, the huge large Quasar group. Each one stretches across scale where the universe should already appear smooth, and yet they exist, or at least they appear to. If these structures are real, they may represent something profound, not just larger versions of the cosmic web, but deviations from the rule that define it, clues that the universe is not perfectly uniform after all. Thus, on a larger scale, there may be subtle variations we have only just begun to detect. But even if future observations reveal that these structures are not as large as they seem, the mystery itself remains important because it reminds us of something fundamental about science. Our understanding of the universe is always incomplete, always evolving. Each new observation has the potential to challenge what we think we know, and the greatest discovery often begin with anomalies, with observations that do not quite fit. Today, we stand at a moment where the largest structure in the universe are still uncertain. where the boundary of cosmic structure are still being mapped, where new telescopes are preparing to reveal the universe in unprecedented detail. In the coming decade, astronomers may finally determine whether the cosmic is truly uniform, or whether it contains hidden patterns stretching across billions of light years, patterns that could reshape our understanding of how the universe formed and evolved. But regardless of the outcome, one thing is certain: the universe is far more intricate than it appears at first glance. Beneath the simplicity of the night sky lies a vast and complete architecture, a network of matter shaped by gravity, dark matter, and cosmic expansions, a structure so immense that we are only beginning to comprehend it. And somewhere within that structure may lie the answer to one of the most fundamental questions in cosmology: is the universe truly uniform,